In part one of the video, we looked at the graphs to see where they were concaved up and concave down. We also matched graphs to where they had the different information to look at see where in the first derivative and second derivative, what that told us about the graph. And then we used the second derivative to determine the concavity. In this part of the video, we'll be going back and revisiting those graphs and finding where their inflection points are, and then we're going to use the derivative to find the inflection points, and then we're going to use the derivative to find the extrema. So let's go back to the graphs that we did in part 1. On number 2, you can see that it was concaved up and down by the green and blue markings, but the point at which it changed concavity, that is called an inflection point. An inflection point is where the concavity changes. So the ordered pair for that point, let's see, I believe we call that about 1.5. X looks at about to be 1.5, and the Y value looks to be about 2.5. So that would be the inflection point.
Let's look at the formal definition of that inflection point. It is a point on the graph of a continuous function where the tangent line exists and where the concavity changes. So at our point, the concavity has to change on either side and a tangent line has to exist. On this first example, you can see that we have a point of inflection. The concavity changes on either side and we can have a tangent line at that point. In the second example, same thing, concavity changes and we have a tangent line at that point. However, in the third example, we do have concavity changing, but we cannot have a tangent line at that point. It's called a cusp or a corner. And at that point, the first derivative does not exist. Remember, the first derivative gives us those tangent lines at those points. So, no point of inflection.
On this graph, notice that it never changed concavity. It was always concave downward. This point right here is a corner. And when you have a corner like that, the derivative does not exist at that point. In problem number 5, again, you can see the blue and the green, so it changed concavity twice. So we have an inflection point here and here. So that looks like 0, 0, and this one looks like 1, negative 1. And on problem number 7, it was concave down the whole time, and so we did not change concavity. We have no inflection points. We do have these 2 points where the derivative does not exist. All right, and then in some other problems we were asked to determine the concavity using the second derivative. I just wanted to go back and look at this example and show you that it did change concavity. It was up, and then down, and then up. And so when x was 0 and x was 3, you would have inflection points. And so what you could do is you could come back to the original function and say, all right, when x is 0, what is y? And you'd plug in 0 for x, and you would get 8. So that would be one inflection point. And then you could say when x is 3, you would get y to be negative 67, and those would be your 2 inflection points because concavity changed. On this example, we found the concavity and noticed that it was always concave downward. So even though this point was undefined, that is not an inflection point. So now let's look at, without a graph, how can we determine the inflection points? Well, of course, we have to find the second derivative, and then we have to find where that second derivative is either equal to 0 or it does not exist. And then we do the number line and putting them to the right and to the left. And then if there's a change, then we're going to go seek out that actual point on the graph. So very similar to part 1, we're just taking it one more step. Let's look at, say, problem number 53. I'd want to find the first derivative, then the second derivative, and now I need to find out where that equals to 0. It always exists because it's a polynomial function, so I'm going to set this equal to 0 and factor out a GCF, and set each factor equal to 0. And now I'm going to do the number line to see, does it change signs across these numbers. So let's see, -1, I'm going to pick a +1, and then inside here, 1/3. Now don't panic. Again, you don't have to do the actual arithmetic. You do get to use a calculator. You just need to know, is it positive or negative? And so we're going to evaluate the second derivative at those numbers. So this first one's going to yield positive 36 plus 24, so that's going to be positive, I think, 60. So that's definitely going to be concaved up. This next one, all right, I'm going to have 1/9 times 36. That's going to be 4 minus 8. That's negative, so this is down. And again, you could have chosen a decimal. You could use 0.3. Anything between 0 and 2/3, and 2/3 is approximately 0.67. And this one's going to be 36 minus 24, which is 12, which is also positive. So we know it's concaved up, and then down, and then up, and an inflection point is where concavity changed. And so I know x is 0 and x is 2/3 would be part of my inflection point. But you have to go back to the original function to figure out what that y value is, right? So when x is 0, what is y? And when x is 2/3, what is y? And please don't use a decimal here. All of your scientific calculators should be able to use a fraction to evaluate that, right? So when I plug in 0, I'm going to get 1. And when I plug in 2/3, I get 11/27. And so those would be my two inflection points. Let's look at problem number 55. And I'm just going to use x's here. It just makes it easier. That looks like the cube root, and I'm going to change that to an x. All right, so this is good practice in remembering those exponents. And I think it would be helpful to rewrite this with positive exponents. And so that's our second derivative. So we want to know when that second derivative equals to 0. And as you recall, that would be never, because a fraction can only be 0 is if the numerator is 0. But it's undefined when x is 0 because you can't divide by 0. So it's undefined at x is equal to 0. So that's the only point we have to test on our number line. So we want to test to the right of it and to the left of it. And remember, we're testing the second derivative. Okay, remember this bottom number means to take the root. So the cube root of -1 is -1 raised to the 5th power. An odd amount of negatives would stay negative times 9, so that's going to be -2 over -9, which is positive. So we would have up here, right? Then we have -2, and all that is positive. So this is negative, and so that means that would go down. So we do have one inflection point when x is 0. So this math is going to be a little bit easier. I'm going to come back to the function, and when x is 0, the cube root of 0 is 0. So that would be your one inflection point. When you get to these problems on the homework, they may be some of the same problems that you used when you were asked to find the concavity. So I'm going to go back to problem number 45, and even though it's asked us to do the concavity, I'm going to continue that problem and find the inflection points. I'm going to, first of all, rewrite this. So let's rewrite this with our negative exponents. So that's going to be positive 6, right? So we have a 6 over x to the 4th. So very much like the previous example, it's never equal to 0, but it's undefined at 0. So I would just evaluate it with one number above and one number below. And you can hopefully see that these are both positive, so it's always concaved upward, so there would be no inflection point. This next part is what's called the second derivative test. It allows us to find the relative extrema, those minimums and maximums. But you're going, well, I just did that in a previous section, and that is true. Okay, you can look at a graph and say, it's increasing and then decreasing, and so that was called our relative maximum, or vice versa, and we got a relative minimum, and we used the first derivative. We can also use the second derivative to find those maximums or minimums, because When you have a concave upward, that's going to give you a max, that's going to give you a min. And sometimes the second derivative test is easier than going through the first derivative. So let's just see what we have to do. We have to compute the first and second derivative. We have to find those critical numbers, and remember that's when the first derivative equals to 0. And then we're going to compute the second derivative at each critical number. All right, now the key thing is this part C. If that second derivative equals to 0 or does not exist, it doesn't tell us anything, and we've got to go back to using the first derivative anyway. All right, so let's look at some problems. Look at problem 65. All right, so we need to compute the first derivative, and we need to find when that first derivative equals to 0. Then I need to also find the second derivative, and it says to, on third step, compute the second derivative at each critical number C. So I need to evaluate the second derivative at 5 and at -1. And what does it tell us to do after we compute it? It says if the second derivative is less than 0 or negative, then there is a maximum. Now why is that? Well, if the second derivative is negative, that means it's concaved downward, and that would give you a maximum. If the second derivative is positive, that means it's concaved upward, and it would give you a minimum. And so, let's see, since this was positive, it means it's concaved up, and that's a relative minimum. This is negative, so it's concave downward, and that would give you a relative maximum. Now let's see, it says find the relative extrema. That is not just the x value, that is the x and y value. So our relative extrema is found by taking the x values and going all the way back to the original function to figure out those y values. And yes, I'm going to use a calculator. Hopefully I pushed the right numbers in my calculator, and so these would be my relative extrema for problem number 65. Let's look at number 71, and again I'm just going to be using x's. It says take the first derivative and need to set that equal to 0. So that's going to be interesting. So I have 0 2x plus 16 over x squared. Now how do I solve that for 0? Well, I want to get rid of the fractions, so I'm going to multiply through by the least common denominator of x squared, and 0 times anything is still 0. Okay? That looks a little bit better, so I can subtract 16, divide by 2, and then take the cube root, and yes, the cube root of -8 is -2. All right, so the first derivative is equal to 0 when x is equal to -2. Then it says to take the second derivative and evaluate the second derivative at the critical point that we found from the first derivative. And of course that's going to be positive, so that since it's the second derivative, a positive second derivative says it's concaved upward, so that's going to give me a minimum, okay, and the minimum value is when x is -2, you have to find out what y is, and you have to go back to the original function. So if I go back to the original function, that should be 12. So this would be my relative minimum. Make sure you understand the directions. When it says use the second derivative test if applicable, that you need to know what that is, which means you find the first derivative, you find the critical numbers, and then you evaluate the second derivative at those critical numbers.